Hello everyone, this is Jain, an aspiring data scientist. Today I would like to discuss EigenFaces example as you can see on the screen, which is very important to understand the core essence of PCA, how we are reducing the dimension, and what is the significance of eigenvalues and eigenvectors, why we are using them. I will explain EigenFaces example using the MATLAB code. First, I will demonstrate what is the problem and what is the data set and what are the data set contains. How many images are there? Let's get into it. See, in the data set, we have 36 unique persons images, and each person has 64 images of their own in different lighting conditions. It means we have 36 unique persons, and each person, let's suppose here is the first person. I think you can see my cursor. The first person contains 64 images in different lighting conditions, and each person also contains like this. Means we have 36 into 64 images. 36 into 64. See, I have written everything. Total persons are 38 in this code, and the 36 images of the unique persons we use for training purpose, and the remaining two persons for testing, and each person can 64. Total we have 2432 images in the data set. And how we are able to write these images in a matrix form, let's see that. See, and each person, see, I will show you. And see, let us suppose this is one image. It contains 192 pixels height and 168 pixels width. Means how many pixels are there? 32,256 pixels are there for each person. Now we flatten this image to a column vector. Means which it contains 32,256 rows and one column. One image, it is one image, right? Like that we create the matrix having how many images? 2432 images. Means what will be the shape of the matrix? See, 64 images of one specific person, and 192 is a 192 pixels height and 168 pixels width. And see, person 1, one column vector, person 2, second column vector, person 3, and average face is there. How we construct average face and how we decompose the given x into eigenvalues and eigenvectors using singular value decomposition SVD. How we are able to do that, and we will also visualize how the eigenvector looks like. It is a vector, right? Each column is nothing but a vector. How it is looking like. That is why we learn some concepts like in vector calculus also we have curl, divergence, but we don't know the significance of them. But using the physical interpretation, we have to use some sort of physical example. We have to take some sort of physical example so that we can interpret them. In a similar way, to interpret PCA, we are taking the eigenfaces example. Let's get into the code part. I'm going to MATLAB. I'm going to MATLAB. I think you can see the screen. I think it is visible. See, in faces, we contain 32,256 rows and 2410. Why 2410? We have to, because in faces there are 38 images. See, let I will multiply. See, 38 into 64. Each person contains 64, right? I think we can you can see the command window on the right side. It is giving 2432, but there are only 2410 here. It is because I will show you this n faces. N faces. See, for first person there are 64 images. For second person there are only 62. Like that for some persons, see, for the 12th person there are only 59 images. because of this because of this we are getting 2410 here. See, eigenfaces, this is our matrix. It contains 32,256 rows and 2410 columns. Each column is a image. I hope you understood. The first 64 columns are the images of the first person in different lighting conditions. First 64 and 65th to 128 are the images of the second person in different lighting conditions. In the similar way, we have completed this matrix. Means we have represented our data in a mathematical form so that we can able to train, so that we can able to visualize, so that we can able to make conclusions from it. I hope you understood. Now let me close this and displaying. Now how we are displaying? We have the faces matrix. From this we our aim is to extract the unique person. First 36. We are displaying the unique 36 persons. Why we are displaying only 36? Because we are only training these 36 persons images in different lighting conditions. And for testing purpose the remaining two will be used. You can see here. What is this code is all about? I have written. Let me open it. See. I hope you understood this. And this is a faces matrix. Faces variable contains 32,256 rows and 2410. How each image is nothing but a person. Okay, see, displaying image. Let us suppose, okay, I will I will see. We'll make it side by side. You can see. For I is equals to 1, I am taking I is equals to 1 and count is equals to 1. N is nothing but the pixels height. In each image there are 192 pixels height, 168 pixels width, right? That is nothing but n here, and m is 168. And I am taking I is equals to 1, j is equals to 1, and I am going to this for loop. I have just inserted I value, j value, and I got like this. See, at the first we are constructing 192 into 168 size. This one, see, 192 into 168. This whole image contains these many pixels. 192 into 168. We are multiplying 192 into 6 means, because we are taking 6 persons in a row. See, 6 persons height, 6 persons width, right? So that we are constructing one image. In that image we will be having 36 images, and each image contains 192 pixels height, 168 pixels width. Now see, I have inserted I equal to 1, j equal to 1, and you see all the persons. See, all rows, it created rows as 192 to 168, and columns 1 to 168. And I just inserted. You can see faces is the variable where all the images are present, and I just substituted, and 1 plus like this you got. All persons is equals to reshape. We are doing the reshape because it is contains, see, faces contains all the rows. We are taking from faces. We are taking all the rows and the first image. Why we are taking the first image? Because the first image is the first unique person image. We are taking where we are able to get this image from the faces. And if we keep j is equals to 2 and count is equals to 2, see, I have done that, and I have inserted those all persons 1 to 192, because the height is same. The height from here to here, the height is same. We are taking the second image, unique image from the faces, and inserting in this complete image as the second one here. The height is same, right? Because of that, we are taking only from 1 to 192, and 169 to 336 means the second. For the second person there are 168 pixels again. For that we are giving space in this matrix from here to here, and we are also again reshaping it so that it will become an image. See, you can see 1 2, and here we got from, see, sum of n faces 1 is to 110. It means the first image contains 64 images. For first unique person contains 64 images of its own in different lighting conditions. I'm adding that because this will give that only. N phases contains, as I showed you before, N phases contains, I will show you again. N phases, see, N phases 64 here. We are adding that 64 so that I will get 60 from 65th image is a unique person, right? So that I will get that. 65 is a unique person image. First 64 images in the faces are the you first person images in different lighting conditions. 65th is the starting of the second person image, unique person image, which is unique. So that I am getting, so that we are able to get these unique 36 persons images. I hope you understood. And then see, it is done that similarly we have other 36 persons from the faces, from all persons we add this to all persons. See, we created a one variable where we store all the persons that we want to train from the faces like this. Now we are just trying to display the first 64 images of the first unique person. See how they are looking like. This is just the code, guys. I haven't written it because it is your work. I'm giving the homework for you. Understand this code. Just write like this. Just go to the for loop and understand. Take count equal to 1, I equal to 1. Just go into it. And you will be understanding very clearly. We are taking the first 64 columns of the faces so that we are able to get this. Because the first 64 columns are nothing but the first person images in different lighting conditions. We are taking that itself. And I also done the second person. And I will go to I will make it big and see. You can see here. Now training phases. See, training phases. We are taking only the 36 people images, 36 persons, and each person has 64. Don't forget about that. And we are also taking each person has 64, right? We're also taking that. Let me see. And we are subtracting from the, we are also constructing the average phase. Why we are constructing it? Because if we able to construct it, and if we able to remove it from the training phases, then the model will know, okay, I have the unique person images and which contains the unique features, not the general features, so that I will learn clearly and able to build a mathematical model so that I can classify a new image or I can reconstruct a new image. It will be very easy for me. See, guys, what is the use of training the general features to the model? There is no use, right? So that we are subtracting it. How we are able to do that? Doing it. See, we'll show you. See, in phases we have 38 unique persons. Testing images are also included, but we are taking only the 36 persons for training. Just write this code, you'll be understanding it. And the average phase, what is the average phase? See here, average phase is equals to mean of training phases comma 2. Something is written here. I have written, what is that? Mean of training phase comma 2. It is nothing but the mean inbuilt in MATLAB. In mean, if you take a mean, if you take the mean function, it's inbuilt properties. If we take as comma 2, see, I have taken here training phases shape is this. And if you take the size of training phases comma 2, it means the all the columns of the phases. 2282 columns are there. Why 2282 are there? Because 32 into, guys, I hope you are understanding, 36 into, if you don't if you have any doubts, write in the comment section. 64, I'm getting, see, 2304, but there are only 2282. Why? Because some persons don't have all the 64 images in different lighting kinds. They may have 59, they may have 58, they may have different like that. I hope you understood why 2282 are there. First 36 persons in different lighting conditions. I'm getting these many images 2282, and we are taking the mean of all the columns, all these images, and we are creating one column where we are taking the mean of all these columns. We are adding all these columns and taking the mean. That's what we have done. See, mean of all the columns, and we will get one column. Means nothing but one phase. That is our average phase. As you can see, it is our average phase. I will show you. I hope you understood. But there is one problem here. One problem here. What is that? I will tell you. See, when we are subtracting the training phases, all the training phases we have, and we are subtracting with the average phase, so that we will be having the unique phases. The into average phase into ones, means we are constructing one matrix, unitary matrix, where the matrix contains what is it? I will see. We are constructing one matrix. See, we are subtracting the training phases from the average phase, means shape should be same, right? When we are subtracting, I think you know the basic matrices, how the matrix subtraction will be done. The shape should be same, but how we are getting the shape? Because as you can see my cursor, the average phase dash is equal to the average phase into the a matrix which contains 2 to 8 columns, and all are ones. Because we have to subtract this average phase from the each person, from the each phase, right? From the each phase that is present, we have to subtract it, so that the average phase should be of the form 2 to 8, 32,256 into 2 to 82. This should be it, so that we'll be subtracting every phase from it. I hope you understood. And from that I have, see, I have, and now we are doing SVD decomposition. We are giving, just take the x, it will take the x and it will give u s v. U is the eigenvalue eigenmatrix, v is also eigenvalue eigenmatrix, and I have done that. See, this is how the average phase of the 36 persons in different lighting conditions looks like. And I have, see, what is the shape of u? What will be the shape of u? U will be of the shape of the same as the shape of the x. See, u, what is the shape of u? 32,156 into 2 to 8. 2 to 8. See, its shape is same as that. Shape is same as that. Now let me discuss the further code. See, now we are able to visualize the eigenfaces as well. That is the power of eigenface example. When we are dealing with different problem statements, like in iris dataset, we have sepal width, sepal length, petal length. Different four features are there, and the label with these features, the label column, which whether it is vertical or different flower images are there. When we construct the eigenmatrix for that, we don't know the each column of the eigenmatrix looks like. We cannot visualize that. We cannot interpret it. But here we can do that. Before going to this part, I will show you how the shape of USV have determined. I will show you. Let me show you. See, you can see we are decomposing the x, our x, to USV. U and V are the eigenvectors which contains the eigenvectors, or the matrices which contains eigenvectors. Our shape of our x is 32,256 rows and 2 to 8 to columns, means 2 to 8 to images. It will be decomposed in this fashion. See, if you have a general m by n matrix of x, it will be m cross n cross n, and n cross n. Have you understood that? Now let me go to the code part. And see, write this also, guys. This is also homework for you. Take a paper and pen and go to step by step, where we are taking, see, this is our u, it looks like this, but we don't know what is each, we don't know how they are. We are trying to visualize them, because each column is nothing but a image. How we made an image to a matrix, we are now have to reconstruct an image from the matrix. See, we have to take the first column, we just have to reshape it to 192 cross 168, then we are able to get this image. It's a code, very simple code, guys. Write it, take a paper and pen and write there, you will be understand completely. See how it is look like the first. See, and we know that in eigenmatrix, the first column vector has high preference, means it contributes, it contains lot of information, because the S matrix contains the columns or the values where the first column has more, because this vector has corresponding eigenvalue maximum. We arrange the eigenmatrix in such a way that the vectors in the eigenmatrix are represented in such a way that their eigenvalues are in decreasing manner. I will I will see in the next video. I will create how, why we have to think about eigen vectors and eigenvalues. I will go through it. What is relay constant? What is the problem formulation? How we will be solving that? I will go to that part in the mathematics part in the next video. But I'm trying to get the insight, the intuition behind PCA. How we are going to build, what it actually doing. See, we have just see the first column vector is showing the general outline of a human face. See guys, general outline, how a general face. See, we can able to see the shape of the image, shape of the face, and eyes are present at this place, nose is present at this, but we don't know the exact features. When we are going to the other columns other columns in this eigenmatrix, we're able to see the unique features. See how we can see here how the nose is constructed, how the nose is unique, different noses, and how the we can see the eyes as well. We are able to see the inner features of the face when we're going to the right side of the eigenmatrix u. I hope you understood. We are able to visualize that. Now we are trying to reconstruct. See, this is a 37th person. This is a test image. Here is a test image. Here is a test image. Now we are our aim is to reconstruct this test image from the eigen faces. We have faces. These are the faces. See, means eigen matrix contains eigen faces. Each face is nothing but each column vector, right? Now, how many column vectors we need to reconstruct this face? This face. See, when we are using the first 25 columns of the eigenmatrix, we are able to reconstruct this image in this fashion. But how it able to do that? Let's see. First, let me tell you the intuition of the code. See, we are adding. See, test face. We are taking the test face from this test face from the faces, and count is equals to 1. See, again we are subtracting the test phase from the average phase, so that we because we want the unique features of this. See, when we want to reconstruct this similar guys, let us say you are going on a road and you saw some person, and you are able to recollect who this person is, like Jayant. How you are able to recollect it? How you are able to get the image? Because the unique features that present in the person that you saw are similar to the unique person's unique features in me, right? If the unique features are same, then we can conclude, okay, this person is looking similar to that person. In a similar way, we our aim is to reconstruct one image, one test phase. Let us take my image. If you want to reconstruct my image from the eigenmatrix, we have to just multiply. That is the power here. We are able to, on doing the dot product, we are able to get that. See, we are taking the unique features of the test phase, and see, see, I will ask you one question, guys. See, the reconstructed face is like this. We are adding the average face because the face should contain the average features also. The border of the face, the construction of image, the eyes should be represented at a particular position, nose will be at a particular position in the face. The average face must be needed. What do you think about this code? What it actually adding? It's adding the similarity, the unique features of this person, of the test phase. What are the, see, we are just doing the dot product, but the dot product has the more significance. On doing the dot product of the columns of the vector that present in the eigenmatrix with the test phase, we are able to get the unique features of the person of the test phase. We are able to get the unique person, unique features of this test phase that present in the eigen phases, and just we are adding that. See, so that we are able to, if we take the first 25 columns of the unique eigen matrix and we are multiplying with the eigen matrix, you are getting an image like this. But on iterating, see, if you take the first 1600 columns of the eigenmatrix, because eigenmatrix contains, shape of the eigenmatrix is 2282. This is our test data, this is our training data also. X is our training data, training phases. From training phases we have reconstruct, we have we have subtracted the average phase, and we stored in variable x. It is our training data. Means you will be having the same shape, as you can see, 32256 into 2282, without using all the images or all the features in the u. We are able to reconstruct it, means we are reducing the dimension from 2282 to 1600. I hope you understood the dimensionality reduction here. The computation power we are reducing. We're When we are training the model, it will be, when we have more columns, the model will also try to overfit. We're reducing the overfitting. See guys, we are taking this image and we're able to reconstruct it from the eigenface. What does it mean? Means the eigenfaces contains the unique features. See, when we are doing the dot product of the eigenface and the test phase, we are getting the unique features that present in this test phase, which are similar. Means the eigenface you have and the test phase you have, and you are doing the dot product. What does it mean? What are similar in these two? The eigenface and the test phase that we will be getting, right? And we're adding to the average phase so that we're able to reconstruct. And it is very funny, right? See, I will show you. We are able to reconstruct a dog as well from the human faces. I will show you that. See, this code complete, and see, we're able to reconstruct a dog from the eigenfaces as well. See, when we took these first 1600 columns of the eigenface, we were able to reconstruct this dog. How intuitive it is. I see how you are. I think that is the power of eigenvalue and eigenvectors. But what it actually contains, it contains the eigenvectors, it contains eigenmatrix, contains the vectors which can give the high variance, which has a high variance on projecting the training data on it. I will go to, I hope you know what is, how PCA works. Where, see, before going, first I understood this example, then I understood the PCA. It is not like that first I understood the PCA, then I came to this example. No, I understood this, then I, okay. In eigenmatrix, we contain the vectors, unit vectors, which by which on projecting the training data we will be having maximum variance. Maximum variance means, maximum variance is nothing but the unique features here. We're able to interpret it geometrically using this example. I hope you understood, guys. Then see, now we are projecting the principal component. What are principal components here? Principal components are nothing but the other basis to represent the data, the given x. Given x, we are able to represent. If we represent, then we will be having maximum variance. Maximum variance is nothing but getting unique features of that person. See, when I have projected the test, when see I have taken, I will tell you. See, I have taken two images from the faces. These two images are the, I have taken from the faces. Say, second and seventh image I have taken from the faces, and then I have taken two eigen faces, 5 and 6, from the eigen matrix. I have just done the dot product. I am able to get the points which are not overlapping, so that I can build a model like this. I can build a model like this, right? If you give a new image, it can tell, okay, this person, we can cluster it. If you give a new image, and it will tell, okay, this person unique features are similar to this person unique features, so that we can cluster them. See, PCA is the unsupervised machine learning technique. We don't need the labels as well. See, that is the power on projecting, because the projecting, when we are projecting the unit vector on a vector, that vectors we chosen in a way that on projecting we will be having maximum variance. How we will be choosing? Because on doing the, see, when we are solving the problem formulation, we got to know that when we project our data on the vector, which on a vector, so that we'll be having maximum variance we have chosen. And they, and the mathematicians found that if we able to find the eigenvalue and eigenvectors from the given x, then the problem is solved. Those are the vectors present in u and v that contains the high variance unit vectors. On projecting we will be getting high variance. I hope you understood. I have connected this to the concept of the PCA. What is the aim of PCA? The aim of PCA is to find a vector, a unit vector on which projecting the given data will be getting maximum variance, and that variance we are able to get using U and V eigenmatrices. I will share this code in my GitHub. I will give the link in the description. You can go through it. And if you have any doubts, please write in the comment section. I'm very happy to answer them. I hope it is understood. Thank you.